Okay, thank you everyone for coming. I'm very pleased to be here to present to you about my company. So my name is actually Grey Tan. I'm the founder of TinyMOS. So in case you're wondering what TinyMOS is, I'll go into that. Okay. So, I clicked twice. Okay, so TinyMOS is a space imaging company. We are making the world's smallest astronomy camera, which is called Tiny1. So we have been described by ex-NASA scientist Dr. Bidushi as a Hubble in your hands. I'm pretty sure she doesn't mean that we are as advanced as Hubble in our imaging capabilities, but I believe she's actually saying that we have the same aspiration as Hubble. We want to bring astronomy and astronomy imaging to the masses. For us, it's on the individual level, and for Hubble, it's across the civilization. So how did this company begin? It began when three of us founders came together. I was actually a student back in 2014, and that's where I got into astronomy. So I was actually a very avid photographer. I took a lesson by Dr. Phil Chan. So he actually told us a lot of inspiring stories about physics. So the one that I remember the most clearly is that at the start of the universe, there were only very light elements. For example, hydrogen and helium. Everything that actually is heavier than hydrogen and helium formed at the core of the stars through a process called fusion. And we all know that we are not made of only hydrogen and helium, and therefore actually all of us are stardust. So this physics story actually inspired me to find out a lot more about this physics, about space and science. So I took even more modules in NUS in physics. The second module I took was called Sky and Telescope by Dr. Abel Young. And through his own hobbies and interests, he taught us a lot more than what is required in the syllabus. And that's how I learned about astronomy photography. And during the same period of time, I was actually doing a business module. And that's where I met Ashpreet, my co-founder. And we were doing a module called New Product Development. And we came out with this idea to make a camera for the masses to be able to capture astronomy without a hindrance of cost as well as weight. So between the two of us, we didn't have enough astronomy or physics knowledge, and we roped in my high school friend, Liwei over here. Okay, so he's a stellar individual really. So he actually was the CTO of a multi-million-dollar startup before he even joined us. And that was back in Silicon Valley, and even till now, he hasn't even graduated. So coming together of three friends founded this company. Okay. So, Leo, just 1 second. Okay, so I was watching this video when I was doing the physics module under Dr. Abel Young, and I looked at this video of the Milky Way, and I always wondered, is the Milky Way real, and can we actually see it through our own eyes? And I hope that when you're watching this video, you have the same questions as me. And I'll let the video do the talking. Okay. So I was very inspired by this video to actually go and find out, is this actually real? Is this actually visible through my own eyes? And through the help of the NUS physics department, I met a very helpful person known as Remus. I think a few of you guys here know him as well. So through his help, I actually went on a tour to Mersing, just 2 hours drive away from light polluted Singapore, and I managed to capture this image. This is the image of the Milky Way, captured just 2 hours drive away from Singapore. And this is the very first time I've actually seen the Milky Way from horizon to horizon. And it's just so awe-inspiring that I've decided I want to pursue this further. But I also want to share this experience with my friends and family, and that's where I realized that there's this problem. So remember I told you I was a professional photographer. So I happen to have one of this camera, and this is what I captured it with. And this is from a second-hand shop, and it still costs $4,600. And to be able to capture images like this is about the entry price to be able to do that. So a few problems here. First of all, the camera equipment is really heavy, very expensive, and very complex. Most of us don't know how to operate a camera like that. So in addition to that, you still have to actually know more about astronomy to be able to capture images like those. So basically, you have to go to university and learn from a professor, basically, to capture images like that. So we want to simplify that. And this is the... Oh, why do I keep pressing 2? Okay, so this is the prototype idea that we have. To create a small camera that simplifies the capture process and helps you identify the astronomy features that you want to capture, so that you don't have to carry so much weight, go in depth into the astronomy and photography knowledge, but be able to capture great images like that. So we're wondering whether something like this could be made, and we brought this very small scientific camera known as the ZWO ASI 120 MC. The sensor was the size of my pinky's fingernail, and we managed to capture an image like this. This is definitely a very low quality image compared to what a DSLR does, but it proves to us that at 1/7 the size of a DSLR, we are able to capture the Milky Way regardless, and we were inspired to actually pursue this endeavor. So after after 18 months of development, raising funds and building prototypes, we managed to capture this image, the next image, okay, with a camera with the same sensor size. And this is approaching a standard of image quality standard of a DSLR that costs a few $1,000s. And the target price we are actually going for this camera at launch is $500 US. And not only can it capture great images like this, it will also tell you where to point your camera so that you don't have to have in-depth knowledge of astronomy just to be able to begin. And after 18 months of development, this is how the camera is going to look like. We've engineered it out of aluminium for durability as well as cooling purposes, so that we can improve the signal-to-noise ratio as much as possible. And we really wanted to bring this product to the masses. That's why we went to US, California, to go for a TechCrunch conference where we actually sought to get in more interest as well. And along the way, we captured this image, time lapse. Okay. Okay, so I wouldn't say that this exceeds the performance of a DSLR, but I would say that we've come close to the performance of the DSLR at a fraction the weight, the cost, as well as the complexity. So apart from imaging Milky Way, we are also targeting to capture northern lights as well as the moon and the sun. So this video is captured from the F1 pit building in Singapore, with a lens the size of a can of Coke. So notice that you can actually see the craters within the craters on the moon, and that's how sharp we can actually go into. Okay, I thank you for listening to my presentation. I hope I have I hope I have developed a product that will help you to explore the cosmos and to inspire you to find out more about astronomy and physics. Yeah, thank you. Okay.
So thank you. Any questions? Okay, so any urgent question, important questions? Okay, so you have don't have a mic, right?
Is the optics specific, or is just the lens that you bought? The lens.
Okay, so the camera is designed for a wide variety of purposes. So the wide angle was taken with a lens that is about the size like this. So we are actually using a CS mount standard so that you can put as many accessories as possible. So with the CS mount lens, you can capture wide field images like the Milky Way I've shown you. Then for the lunar image, we actually adapted to a Nikon reflex lens, 500mm, which allow us to capture an image of the moon. Yeah, does that answer your question?
What is the sensor, the manufacturer of the sensor?
That one I can't disclose right now.
So when can we buy the camera?
So do remember to support us on Indiegogo. We are coming to Indiegogo in first quarter 2016. In the meanwhile, if you want to keep getting regular updates, do subscribe to us at tinymos.com. Okay. Okay.
The camera body itself and the lens is interchangeable.
That's right.
Okay. Okay. Thanks.
Is there a way to turn the volume down because it hurts the volume? Speaker volume too high.
Oh, okay.
Okay, no problem.
The sequence with the moon, is there some post-processing after, or is it straight from the sensor?
Okay, so to be honest, we had some post-processing done. So I think there are some astro enthusiasts over here. They will let you know that actually you won't be able to take this kind of image in a single shot. And the limiting aspect is the atmosphere actually. So the movement of the atmosphere prevents you from getting a sharp photo. This was taken 900 consecutive shots combined into a single image. So right now this is captured at about 3 frames per second because we are using a prototype. When we complete the development, we are aiming for at least 60 frames per second. So that will take you just over 10-15 seconds to complete a sequence like that. Okay, yeah. Okay, I'll take questions from this side. Yeah, go ahead.
Sure. What's different when it comes to astrophotography as compared to normal photography? Like, what's special about the camera?
Okay, so he asked, what is special about the camera? What's the difference between for astro cameras as well as everyday camera? So the difficulty in astrophotography is that you have to be able to capture photons effectively because apart from the moon as well as the sun, most of these objects have very low luminance. So if you expose your sensor over a long time to capture the photons coming from these distant objects, you have to be able to separate your noise away from the actual data. So there is one of the key challenges, and the difficulty in shrinking everything to this size is the fact that once your sensor goes really small, your collecting area is very little. So we're actually getting images of these really dim objects from the sensor size of my pinky's fingernail. Yeah, thank you.
What's the resolution in pixels?
Can we let him know the pixels? So I think right now we cannot disclose the pixel size, but would this actually be sufficient resolution for you?
Just curiosity.
Okay.
How long does the processing take after you captured the 900 pictures?
Okay, so processing wise, that's one of our key innovations. So in terms of noise reduction, we want a very responsive camera. So I think one of the leading ways to reduce noise for long exposure is called dark frame subtraction. So if you were to expose for the Milky Way for 30 seconds, you have to capture 30 seconds of noise data by covering the lens. So this creates 60 seconds for a single shot where you collect data for 30 seconds. So what we do is that when you're charging your camera, the camera is actually calibrating for that and storing it into a memory module. and we use that noise reference to do the reduction, so that your camera right now only takes a fraction of the 60 seconds. I think you'll probably take about 2 to 3 seconds after each capture to do the noise reduction. Yeah.
And then in the camera you have the picture, so you don't need to do the calculation on the computer afterwards, but it's like...
That's right. So I think I describe this as the world's smallest astronomy camera. I think it's more accurate to say that it's the world's smallest standalone astronomy camera. So there are a few cameras out there, for example, those made by Point Grey. They are actually smaller than us, but those require a laptop to bring along, and that makes life a lot more difficult. So what we have done here is that we actually attach a screen at the back of it. It has a point to star system, which tells you where you are pointing. So there's a star map overlay over on top of what your camera sees. Yeah. Okay. Any other questions?
Is there an FPGA inside? Are you recruiting people?
Actually, I'm quite curious which occupation are you from? You
I used to work for a company designing some thermal camera.
thermal camera from FLIR?
Actually, the lens, the sensor, the embedded system behind it is quite similar.
Yeah. So actually, when we began our development, we have looked into different platforms. The very first one we've looked into was actually FPGA. That was one of the highest performance processors in terms of parallel processing. However, we found out that FPGA actually consumes too much power, and right now we are actually using what do you call it? Okay, we are using a system on chip to do the processing in software, but this system on chip has additional modules that actually does image compression rapidly. Okay. Thank you.